So what I'm doing today, I'm doing the last year exam paper, right? So if you look into the exam paper for last year, the problem number 1 is yeah. So So it's good to do it in a day like this. So it's easy to do. Yes. And then you get once you work on those things.
So if you do the x parentheses.
Right. Why is saying? Okay, so here is the question, yeah? So it's an open-ended pile. So open-ended pile means, what does it mean? What does it mean? Open-ended pile? It basically means it's a steel tubular pile. So it's a steel tube rather than a closed end, right? So in that case, these piles are typically used in any offshore applications. Offshore applications or very soft soil. And good thing about these piles are you have a very high quality control. Because you know that there's a steel pile, you're putting it in the ground, very good quality control, right? So the pile would look like, let's take a small section. The pile, that is the pile section, right? And what is the wall thickness? 63 millimeters, right? And the good thing is that you can drag the pile very easily, quite quickly actually. So you can do the whole piling operation very fast, right? Now, to work out the capacity, there are two important things. One thing is that when you have the pile driven, you can have a case where it will drive. So in one case, you will have soil in the pile, right? So you can have soil within the pile, inside the pile. What is this case called? Plugged or unplugged? Unplugged. So this case is unplugged pile. So unplugged. That means there is no plug in the pile. It doesn't form a plug. And I will do another case, which is In another case, there can be a small plug forming here. So what happens, the plug forms here and then the pile behaves as a closed-ended pile, because it forms a plug, and as you drive it, it moves like that, right? So these things can happen, and this is not a plug pile. Okay? Now how do you then find out the capacity? So when you are driving the pile, what's happening, you have soil all around, isn't it? There is a soil here. There is soil everywhere. So the capacity of this pile, when you drag this pile, will be, there are two things, shaft and end bearing. For this case, there will be shaft from outside the pile. Yeah. There is also friction within the pile, isn't it? With inside the pile, right? And bearing only in annulus part, right? So you will have friction in this annulus part, the ring, because the ring is a thick ring, isn't it? It's like a 16 mm thick ring, right? So you have friction there, friction along the ring. So that means if I draw the plan here, let me do up. So this part will be bearing against the soil. Right? There will be bearing against soil. So you have end bearing from this part. And friction from outside and inside. Yeah? And for this particular case, you have the bearing from the total area. So the bearing will be the whole area. And the friction only outside. Yeah? You have the bearing only from here, from the whole area, and from here the friction, right? So you never know which one will govern for your case. Now what typically happens, when you drive a pile, use a big hammer. As you put a hammer on the pile, there is stress waves which goes through the pile very quickly, right? And then it reflects back, the waves come here and again reflects back, partly gets through the soil, again something comes back, and this stress waves creates a vibration and it doesn't let soil to stick to the pile. Therefore, when you drive a pile, it is normally drives unplugged. because this vibration doesn't let the soil stick to it. However, once you put the pile in place, you would normally leave couple of weeks to few months before you load your pile, because once you put the pile, then there will be another contractor will come and bring the jacket or the tower or the transition piece, depending on the application. In those few months, when you drive the pile, there would be pore water pressure developed in the soil next to it. Why? Because you have a high shearing level. You shear a lot. You shear the soil. So around the pile, the soil is sheared. Very high level of shear, very large shear level. In those shear level, you have some particle break. You can develop pore water pressure. It's only localized area. As time goes past, so those pressure gets relieved, they dissipate, soil becomes stronger. So once you leave for a few months, when you come and apply load, it behaves like a plant. But you don't know very precisely what will act. Therefore, when we do pile capacity, we find out both the cases and take the minimum as the capacity of the pile. So you work out unplugged and plugged, and then you find out the resistance. Yeah? Okay? So to do the problem, so is it now clear? Yeah.
Would that be your free body diagram you asked for then?
Oh yes, I will show you that. Yeah, it's basically showing the forces there.
Same thing.
The same thing. So you show that the plugs, plug will have sulfate,
Okay.
and then you have the friction.
Yeah. You take into account like the buoyancy, or do
You
let
take this
water
submerged to it. You take submerged soil bed submerged.
No, I mean it's like the cup pile.
Mhm.
Does it have water inside of it or not?
Inside.
There is
Plug
water.
will inside. The plug will be inside. Because you know that's what we are concerned.
No, I mean like it's you've got the plug at the bottom, and then inside the pile, just tubular,
Yeah.
you have air or you have water.
What?
The water.
Because if you try to
You've
find,
submerged it and it's in water.
because you cannot stop water from getting in, isn't it?
No, okay.
Okay. So, right. So how I would do it? I would do a simple sketch of the whole problem first. So I would do pile length. So this is layer 1. So layer 1 is 3 meters, right? 3 meters, yeah? Then you can layer 2. So 7 meter. Layer 3. Meter, right? So it's good to do So the question asks you to do a, so okay, the shear strength is 0 here and is 480. This is the shear strength profile. (480 kPa), and then you have layer 2 is a uniform kPa, so 480 kPa. Then you have layer 3 is 220. Yeah. In some places in North Sea, you can get a profile like that. A top side quite heavy, strong clay. The reason was that in the ice age there was a huge amount of pressure that created this OCR, the highly overconcentrated clay. And then you had some deposit, the top deposit, and so you can have a profile like that. That's a clay profile, yeah. And to work out the friction, what you need is an alpha factor, yeah. So what you can do, you can make a small table. So it says just reduce the number of calculations, you know. It says just to use the same value of alpha. So you need to work at 2 levels, yeah? At 5 meter. So depth sigma v not dashed, and you can get this SU by sigma v naught dash and alpha. This alpha you can read from that chart given. Yeah? So you can do a small chart like this. So there are 2 values, 5 meter and 30 meter. So at 5 meter, that means at that level, so what is the vertical stress? Yeah, around 45, yeah? 45. So 45 kPa, so 5 times 9. So you can do your kPa, 45 kPa. At 30 meter, you can also get 270 kPa, yeah? And that ratio would be 480 by 45, and here is 220 by 270. And from that you can get the alpha is 277 and 0.554. Right? You got the alpha value, and now you can work out the friction. Yeah? So it's always good to do a diagram like this in your sheet. So you translate all the information from here to there. And then you can start to do the calculations. Also, if you can do in this particular way, you can think about developing Excel spreadsheet that can do it.
That's the alpha method, right?
Yeah.
So would we get tested on the beta method? Just the alpha.
Yeah, if it is given, I will give you everything. But probably I will stick to
Get the equation.
because there's no point in, because it's more to know the important things, right?
Yeah, so this is
Okay, so once you do that, it's also good to work out the end bearing area. So end bearing area, so only rim, because this you can use for your unplugged case. Yeah, the end bearing rim is 0.288 meters squared, and total area is 0.815 meters squared, right? So you can find out the two areas. So this is the ring only case. And this case is the whole area, yeah?
I've got the answer, but I've used 3 layers. I didn't see this in the beginning.
This is just to reduce the number of steps. Otherwise, what happens?
I got 32 meganewton.
And the outside section,
I've
you
got
can
outside.
take the same as the inside section.
And then I've used plug and plug, and I've used the lowest one.
Yeah. Like the
57, yeah, the same. And then I've got 32, yeah.
So it's a big, it's a big difference. So plug gives me a lot less.
The plug is 32 and this one 57.
Yeah, it's basically similar. Either this or you can use the same one.
So definitely, and in terms of question B, 10 marks, I'm looking for this sort of explanation, or just
Just something like this.
for this. Okay.
The ends of the part.
Good? Yeah. Then, what is the next step? Just fill it out. Fill it out, yeah. But depending on where you are. See the same one here.
Oh, okay.
Yeah. But you can rid of the
Pi d
rid
squared,
off from the things there.
but minus the d squared, the internal.
No, yes.
What about the friction outside?
And
And you can also get the end bearing as well. These are the calculations. As API code, the frequency code, is oil and gas code. Thank you for that. But also, even if you can do it, but even if it is nothing, you always consolidate to the shoe. It's for example,
What are we going to use?
So,
and answer 0 is by 220, and you get the A variance, and then you use that and add it onto your steam friction capacity, and you get the total capacity.
So this one is not the total
No, that's just steam friction.
So these are things. Because if it were redesigned,
This is the
it
external.
won't be hundreds of packages. Almost a big. Do something. But then how we get out of this? Who does
So this that's an outlook for this, the most you can get.
Some of the didn't get the job.
So that is
Some of you are doing you're trying to bid for a project. So they only have one more. And so how much it costs us to put a bid. You go and say, oh yeah, can we raise this? They will give you a quote. You may not do it, but you want a job, somebody else will do it. Somebody else will give you some stuff. This guy will do this one, the exchange is, just work on that and give them $10 million.
1.5 to be like to.
If you can say, ask them to make.
Read those. Don't be done with that, so whatever that was, that would be done.
And you say, but what you do, you issue a divorce case, then you, then we do value engineering. And value engineering, that means I will see if I can cut down the cost. So I will investigate, I will put $10,000 to investigate, I will number to see if I can get down the cost. Then you say, do something, but you don't ask too many questions. Then you will say, yeah, they will be, they will ask too many questions. That's why this is the reason. This is the reason. This is the generally how you start that's why the word often set. Yes, at a bigger surcharge. What data will be?
No time.
That's very important. Just go through the rows. Down. What are the designs? Extreme.
Take acid.
Happen
Like calcium acid. Oh, 76. 0.76 minus 0.00 and minus 0.06.
Earthquake and flood to that. This is a generic for in to start with the loads. There is actually you don't have a system where a temperature inside in animation.
It's have you seen a diagram from the well, this case is applicable where it's where this case basically is applicable where you have to come to the we have a wall without the prop, and you're gonna get very big reflection here, but there's no props put in it. What I've in papers it says that when you have, it really depends on the ground here. If you have stick clay and you have a prop, you're gonna get something like in the prop. You're gonna get something like this, where you have because you're gonna get very high diffraction in the middle. And it's gonna, but it really, I don't think it matters. I'll just use what he gave us, and he gave us this one there. He just used this one. No, he gave us this one. This is in the yeah, this is in the notes. That's what I'm thinking for. I've used lecture notes, I didn't use this one. These notes were made by his PhD student, but the lecture notes were made by the person who gave us the example. That's why I thought like it's more sensible to use. But as he said, he doesn't care. Find something. I don't know. I would assume so because he's the module coordinator, so I would imagine he's going to mark it. So. And he said he doesn't care. And according to last semester with him, he doesn't care. So let's just get something. So just write some numbers. Basically, in the lecture notes, you don't even need to use formulas. Basically, in the lecture notes, it's giving you that deflection here, this half the deflection here, similar that. Yeah, I think it's one of the, yeah, so just use this one. I'll just use this. If I use this one, I just going to get half. Do you get a half? Yeah, it's stated in there. It's in the lecture. By zooming, get half in your deflection. Just assume it's half. Or if assume it's half. Or it's just, it have to be half. You just.
Is it the deflection of the opposite from this elastic foundation?
Yeah, it's half of the deflection of the wall.
Okay.
Deflection of the ground.
Not the settlement.
The settlement is half of the deflection of the wall according to his lecture.
How do you walk at the street? I mean, damage category.
I assume the length of the building. It's based on what's currently recording. Where's his
I assume that we will double of this double of this
it's in his lecture, so whatever is here.
What time is it?
But, I mean, you're going to open it with your beauty and it says you everything. So by only having this, you can basically say what everything else is. Basically,
this diagram.
yeah, I've used this diagram. Basically, about the ground settlement, it's, you need to know the ground strain. I did it for my DSEP. So I know how to work it out properly. But it's, don't get me wrong, I spent like a week doing it through my DSO understanding it. So I don't know how to explain it simply. So because I've used that, I've done this about tunneling and the effect of tunneling, construction and settlement on buildings. So it was basically use the horizontal strain, which depends on building length. So just assume the random number of building lengths of 10 and just work out the strain, and then basically there is a chart which tells you the amount of strain and the degree of damage. And then by using this degree, you can But I mean, it's quite, I don't know to what extent you need to implement in this coursework. So just,
Because you need it for the risk assessment, you need to know
Yeah.
how to do the risk assessment.
so I don't know how to,
No, for risk assessment.
Yeah, you need to damage.
Yeah, yeah, but you. It's like what we have to do in the risk assessment.
because, well, I know how to explain this. It's basically, if you have a building which is 100 meters long, and you have like 10 millimeter settlement, it's going to be very high damage to this building because of very long span. But if it's like a 1 centimeter building, yeah, it's expensive. It's going to be zero damage because the strain is negligible on the building itself. Do you know what I mean?
Yeah, yeah, you compare to very long thing.
Yeah. So this where the strain comes into play. So it's even if you have very high settlement, very big settlement, if your building length is very tiny, you can have small strain and 0 degree damage. But if you have very long damage, small settlement, the strain will be very high, so very big damage.
One building that needs to be and then.
Yeah.
So you what about both?
Because the building is going to move with the
Together.
settlement.
So it's based on like the moment and
It's based on the strain. Horizontal strain. Horizontal strain.
Just work out cookies.
But it's very much a graph involving scalding and boarding relationship.
Okay.
BOSCA. But as I said, I don't know. Do not to go or not, because it's going to take you a while to understand. So